Pat Morin is the Deputy Scientific Director and Communications Director of the Ludwig Institute of Cancer Research. He received his BS and MS in biophysics from the University of Quebec and his PhD in molecular biology from Boston University. He has worked for some of the most prestigious universities and research centers in the United States. He joined the Ludwig Institute in July 2022 as Deputy Scientific Director. Daniel Ludwig was listed as the richest American by many publications in the 90s, but the public has little knowledge of him. That is exactly how he wanted it. Mr. Ludwig had the largest fleet of oil tankers in the world. He owned the Princess Hotels, now the Fairmont chain, and many other companies and buildings in New York. But Cancer Institute is his greatest legacy. I'll turn it over to Pat.
Thank you so much, Tom, for this presentation. And it's truly an honor for me to be here today to talk to you about the Ludwig Cancer Research and also talk about our progress on our fight against cancer. So I'm, as Tom just said, I'm the Deputy Scientific Director and Communications Director at Ludwig Institute for Cancer Research. And I'm really, as I said, looking forward to talk to you about sort of the latest breakthroughs and have a discussion with you about some of the innovations in cancer research that are taking place now. I think we're at a very exciting time when it comes to cancer research and the progress being made. But before I do that, I'd just like to say a few words about our organization. And Tom, you've already said a little bit, and I'd like to pick up on what you said and talk about Mr. Ludwig, who is not very well known in spite of all the great accomplishments that he did in his life. He was born in 1897, died in 1992 at the age of 95, and he's sort of widely recognized as the father of the supertanker. He's really the one who sort of came up with the idea that if you carry more oil in one trip, you'll make more money than if you have these multiple smaller trips. So he was always trying to build these tankers larger and larger, leading to what we know as the modern supertanker. He has an interesting story. He started fairly poor. He lived in Michigan, and in the 1910s, as a teenager, he bought a sunken boat. He fixed it, and he started renting it for $150 for that summer. That's when he started his career in shipping, and by starting with this single sort of recovered boat, his fleet grew to over 60 supertankers by the 1970s. As Tom indicated, he shied away from publicity, so he's not really well known today. But even at the height of his career, he wasn't really well known. He was the richest man in America for some time in the 1970s and probably into the 80s, although he was quite diversified at some point after he made his fortune with the supertankers and shipping. He bought some interest in mining, in refineries, real estate. He had several buildings in New York City, farming, hotels, and so on. So because he privately owned all these things, not part of a corporation. He was a privately owned all of these things. So his fortune was a little harder to sort of pin down compared to some other of his peers who may have had sort of stocks, a large number of stocks in certain corporation. It's a little harder to find an exact amount and an exact sort of net worth, but he was widely believed to be the richest man in America at that time. And but in the early 60s, he decided that one day all his assets would be left for cancer research. So a few years later, he founded what was known at the time the Cancer Research Institute Limited in 1971. So that's when the Cancer Research Institute was founded. And later it was renamed the Ludwig Institute for Cancer Research. As I mentioned earlier, he was publicity shy. He didn't want his name associated with this, but I think eventually he was convinced to put his name on the institute. Um, just since it's just a quick sort of overview of his empire as of 1963, and this is only North and South America, but as you can see, he had sort of a marine insurance company in Bermuda. He had 2 luxury hotels, as Tom said. He had a model community, Westlake Village in close in California, just outside of LA. He had a 15% stake in Union Oil, and so on. I could go on. He had the largest salt production plant in the world, I believe, at the time in Mexico. He had a ranch of 15,000 cattle in Venezuela, and refineries in various countries, and so on. So he was quite diversified and quite an empire, even in 1963. He was sometimes the focus of although, as I said, he was not really well known, but there was some articles about him every so often, and it was a bit of fascination about him. And there was an article from the New York Magazine in November 1977, where it just said the richest man in America walks to work. He lived a few blocks from his office, and he would just walk to work every day. But I found this part interesting. In 1977, it stated he's our only multi-billionaire. So in the US in 1977, there were a few billionaires, but he was believed to be the only multi-billionaire at the time. So just stepping back and talking a little bit about the founding of the Institute and the goals of the Institute. So it was founded, as I said, in 1971 by Daniel Ludwig. The goal was to synergize with existing facilities. He didn't want to build a Ludwig Institute to build a building, so no brick and mortar. He really wanted to provide funding with research institute that was, and especially they had to be associated with a medical center, because he wanted to make sure that whatever discovery was made by the institute researchers could be translated to the clinic and have a real impact on patients and on people. So again, he didn't want to build buildings. He just wanted to help existing research facilities. The first branch was at the Royal Marsden in London, and here's the first sort of short article on this in 1971. And the first gift was £200,000 to the Royal Marsden, which is about, I believe, 2.5 million pounds in today's money. And that was the first gift that the Institute gave, and to get the research started. Today, we have 3 branches and 6 centers all over the world. And we fund, the Institute funds research in all areas of cancer science. We don't focus on any particular cancer or any particular area of cancer research. We're really quite opportunistic. We just want to fund whatever is most likely to give significant and impactful results. The branches are funded with the Ludwig Institute for Cancer Research Endowment, which was created after liquidating all of Mr. Ludwig's assets. So a question that's often asked is, why cancer? Well, why did he pick cancer? If you think of Howard Hughes, Howard Hughes sort of, the Howard Hughes Institute is not focused on any particular disease, it's really for biomedical research. But Mr. Ludwig was very particular. He wanted to fund cancer research. And so I don't think this question's been ever quite answered as to the exact real reason why he picked cancer research. But one of his scientific advisors asked him one day, so why are you so focused on cancer research? And his answer was, if you can find a bigger problem that we should focus on, let me know. That was basically his message. And although he wasn't a scientist, I think he was right. Cancer has been a major problem, a major public health problem, but also a major scientific problem. And I think the two go together. We need to solve this scientific problem in order to really address the sort of public health problem that cancer has become. So, as I said, let me tell you a little bit about cancer. So, Mr. Ludwig, as I said, was not a scientist, but he was right when he said it's a big problem. So first of all, cancer is not one disease. This is a collection of over 200 different diseases. Lung cancer is very different from colorectal cancer, which is very different from breast cancer, and so on. So I'll show you in a slide. The next slide will show you and give you an idea of that. But someone might even argue that every cancer is different. Two lung cancers may be very different from each other. Someone may be cured and someone may not. And sometimes the reasons for that are not clear. That basically what makes a cancer cell is that, what makes them different from normal cells is that there's some changes in the cancer cells that allow them to grow out of control and become invasive. So if you look here, you have a number of, this could be any tissue. It's just sort of a nameless tissue in someone's body, and you have normal cells here. And then what can happen is that cancer cell can start multiply here. So the cancer cells are very different when you look at them under the microscope, and they tend to lose, not they tend, they lose the ability to control their growth, so they grow uncontrollably. And cancer cells also invade into surrounding tissue, so they don't remain where they're supposed to be. They grow uncontrollably, and they also invade into neighboring tissues, and ultimately they can also metastasize. So this is the main property of cancer cells. So it's been known for many decades now that cancer cells are a genetic disease. So cancer is initiated through mutations in the DNA. And there's really two generic types of cancer, if you really think about it. You have the solid tumors, which are masses of tissue. Think about lung cancer, think about, prostate cancer, and so on. But there's also cancers of the blood, such as leukemia, and they don't really form a solid tumor. There's just a multiplication of cells in the blood, and up to a point where obviously it becomes lethal. There's really, you'll hear these terms often, and the term, malignant, it simply means that it's a cancer cell. It means that they grow out of control, as I said, and they can spread to nearby tissues. And you can compare this to benign tumors. You also term benign tumors, which the cells can grow out of control to some extent, but the benign tumors do not spread. They don't spread to neighboring tissues, making them benign and a lot less dangerous, obviously. So this is what I just said earlier about the 200 different diseases you have for, melanoma, mesothelioma, oral cancer, so on. All of these cancers are very different from each other, and there won't be a cure for cancer. There'll be a cure for this cancer, and then this cancer, and then this cancer. And hopefully one day we'll have a cure for all these cancers, but there won't be a generic cure, most likely, for all of the cancers at once, because they are so different from each other. Biologically, they're very different. The progression of the disease is very different. The outcome, some cancers are very lethal, others are not. So they're just very, very different diseases. I'd like to just talk a little bit about a very important aspect of cancer is the sort of connection between cancer and aging. It's been recognized a long time ago, but if you look at all cancers, on this graph here, so it's basically the average of all cancer in men and women, and you look at, according to the age, the cancer rate. If you're 20 years old, your cancer rate is relatively low. That's 10 per 100,000 people. So that's a pretty low rate. But as you get older, your chance of getting cancer increases and increases up to when the age of about 80 or so, where the likelihood of cancer is about 100 times more than when you were 20. So there's a huge increase in the number of cancers in older individuals. So this is for all cancers, and basically most cancers follow a similar pattern, although they may be a little different in terms of number. All of the different cancers, colon, lung, breast, prostate, they all follow sort of this general pattern that as you get older, you're more likely to have it. There's a few interesting exceptions here. For example, testicular cancer, for reasons, I think people have some ideas, but reasons are mostly unknown, they tend to peak at around the age of 35 or so, and then the risk of getting testicular cancer goes to almost nothing later in life. And there's other cancers here that that are also have these sort of unusual patterns. But for the most part, the older you are, the more likely you are to have cancer. And I'm sure that's not a surprise. But what's interesting to think about is that the U.S. population in aging is aging. We are definitely an aging society, maybe not as bad as Japan, which is known to be a very a society that's aging very fast and that's already quite old. But our society is aging. If you look in 1900, there was only just about 5% of people age 60 and older that in 1900. In 2030, and just 5 or 6 years from now, it's expected that there'll be over 20% of our population will be 60 and older. So if you think about this a little bit, it means that there will be a very large number of people that will be in that category here where the incidence is much higher. So we expect to have a significant increase in the number of cancers in the coming years simply because of the aging population. So there will certainly be sort of a crisis in trying to treat all these cancers. And I think it's very important that we invest a lot of time and effort and funding into research now, so we have the tools to fight the sort of storm that's definitely, I mean, it's already going on, but it's only going to get worse. In terms of, I'll come back to that in a minute, but I just want to specify those are death rates. Those are cancer rates, not death rates. So the death rates are going down because we're much better at treating and curing cancer, but we still have these sort of rate of cancer going up significantly as the population age. So I like to use this analogy of what cancer is like, and it's probably based on some personal experience and frustration with my lawn, but I kind of see the cancer a little bit like a lawn in a way, and how weeds can take over an entire lawn. So it's these, you can think of these sort of patches of weeds as basically, cancer cells that are about to take over the entire lawn. So what can you do? What can you do to try to prevent that? So if you have a very healthy lawn, you're unlikely to have weeds, I'm told. So that's maybe a form of prevention. You can think of it, I'll just make sure my lawn is very healthy so there won't be any weeds. Or alternatively, if you see a small patch somewhere, you can catch it early. Maybe you can just walk over and pick it up, and then it's not going to cause a problem. It's kind of it's a little bit, so the analogy again is a little bit like early detection. You can find it early, you remove it, it's not a problem. Then if it gets to a larger scale where there's a whole section, maybe where there's a bunch of weeds, well, you can use a shovel and then try to remove it, and that will be a little bit like surgery. You have a cancer, try to get rid of it, and then that's, as I said, the equivalent of surgery. And finally, when you get to something like this, huge areas that are sort of taken over by crabgrass or other types of invasive weeds, then people will often use herbicide, which are in a way like chemotherapy. You're trying to use a chemical that will specifically kill what you want to get rid of and kind of leave the rest alone. And this is what chemotherapy tries to do. So those are kind of the, in a way, the analogy and the challenges of cancer treatment. So coming back a little bit to what cancer is and how it progresses from a normal cell. So cancer doesn't just happen in one event. It takes multiple events, and it takes time for cancer to develop. So if you start from a normal cell, like there's a layer of thousands and thousands of normal cells here, there could be a mutation in one of them, a change or a genetic change, one of them, that allows the cells to sort of grow a little bit out of control. But it's not a cancer yet. It can't really invade. It's just there's more cells there than there should be. So that would qualify as a benign tumor. There's just There's just sort of an increased number of cells. Then if there's additional changes, genetic changes, then maybe this little lesion is what we call cancer in situ, meaning that they have all of these the cells here in the darker green area have all of the features of cancer, but they're not quite invasive yet. They're like cancer, but they're called in situ, meaning they're still where they started from. Unfortunately, a lot of times, additional genetic changes will alter these cells so that they become invasive, and now we have a full cancer. And from there, once you have the full cancer, additional genetic changes again can make these cells extremely invasive and even metastatic, where they can reach a blood vessel and basically go to distant sites. So that's how maybe a lung cancer can get into the blood and end up in the brain. And so that's a result of a series of mutations that can take years. But they can be accelerated by certain events if you think about smoking, for example. So there's a lot of complexity here, but this is sort of an overall view of how cancer can progress from a normal cell all the way to cells that are in, basically metastatic cells. I mentioned earlier a little bit about the number of cases, and I wanted to give you an idea of the cancer problem. So those are estimated new cases for 2024. And this is done, they're actually quite accurate, although obviously we don't know the exact numbers because 2024 is not over yet. They have, the statisticians who do these studies are extremely good, and they're always very, very close. And they mentioned that for the first time, there will be 2 million new cases of cancer in the United States in 2024. That's what is predicted. In men, the majority of the newly diagnosed cancers will be prostate cancer, close to almost a third, not quite a third, but in men it's close to 30%. And in women, most of the cancers diagnosed will be breast cancer in 2024, 32% of the cases. And it's almost 3 times more than the next cancer, for both. And interesting to know that the next cancer for both men and women is actually lung cancer. And if you look at estimated deaths, it's a little different. Although prostate is the most common diagnosed, the deadliest is actually lung cancer in both men and women. Extremely difficult to treat, very resistant to some of the treatments that we have now. So the number of deaths in 2024 is expected to exceed 600,000 this year. It says 2015 on my slide, but that's a typo. This is for 2024. So if you look at the cancer death rates in men, and according to the year, this is quite interesting when you look at this. There's certainly been some cancers that have changed significantly with time. You can look at lung cancer, you can look at stomach cancer, and some cancers that are mostly following a pattern that we would expect, which is stable for quite a long time until we found possibly better ways to treat it. Although some cancers, clearly, we're not doing a great job. Pancreatic cancer, for example, it has remained fairly stable, although this graph is a few years old. We've made some progress on some of these now, but it's been quite a challenge to reduce the death rates from these cancers. I'll come back when I talk about prevention. I'll come back to these two these two patterns. Quite interesting how they change with time. Lung that went up and then came down, and stomach that just gradually came down over from the 1930s all the way to the 2010s. So, and that's the same for women. Death rates, there's been significantly increase in lung and a significant decrease in various cancers, colorectal here, stomach again. But again, I'll come back to this. But it's just to show that the intrinsic sort of cancer, that the death rate is not something that's intrinsic. It can change with time, and a lot of time it may have to do with the environment and the way we live our lives. Although that's only obviously just one factor. So just coming back to what is cancer, but importantly, what is cancer research? What can we do to try to attack this problem? So really, cancer research, there's really 4 phases. I mean, you could probably break this up in different ways, but to me, there's really 4 significant aspects to cancer research. First, there's basic research. You want to understand what these cancer cells are. What are they? What do they do? And why do they do what they do? The only way we can really do something about it if we really understand what they do. You can't fix a car if you don't understand what the parts do. So this is like basic research. It's important that I think we invest a lot of money and a lot of funding in basic cancer research, because then if we don't do that, the rest of the wheel can't really turn. We can't really go to the next step. So basic research, trying to understand what these cancer cells do, what these cancers are. Then the next step is preclinical and translational research. So this is when we have a clue as to possibly we might have a pathway, we might have a target, there may be something we can do to treat cancer. Let's try that in the lab. Is there any way we can do in the laboratory, whether it's in mouse or in cells, or we can do drug screens? How can we sort of take what we learn here to the next step and see whether it's promising at all? If there is some promise at this step, then it can go to clinical trials. This is when we start testing these drugs, these new concepts in human beings. And this is, again, a very important part of cancer research. And then this needs to be implemented. And that's an important part. Sometimes we forget. We may have a great drug, but if it's too expensive for people to take it, or if people don't have insurance to receive treatments, then we haven't made the progress that we should make. So this sort of clinical application part is an important part too. I think probably several of you know this, but it's drug discovery and drug development takes a long time. Starting from the drug discovery part, which I was just talking about here. If you really talk about how we can start screening some drug at this point, we can look at thousands of compounds to really be left with only 250 or so that are viable. And of those, after further testing, there may be only 5 that go into clinical trials. And the majority of those will fail in clinical trials. And for the most part, out of all this, we may end up with only 1 FDA-approved drug over this whole thing. And if you look at the timeline here, this can take up to 15 years. So I think we need to do better to accelerate this whole process. And one of the ways we may be able to do it better one day is using AI. Artificial intelligence might really help us to accelerate this. And we may need to rethink the whole process at some point, but that's definitely beyond the scope of this conversation. So I want to tell you a little bit about the history of cancer treatments. So there's really 5 categories of cancer treatments. First of all, there's surgery. If you can remove the cancer, if you can just plug this weed, from the lawn, that's a great way, and you can often do it. I had a BCC on my nose a few years ago. The surgeon went in, took it out, and that was it. I didn't need any more. And that's over 15 years ago. But sometimes you need more. Sometimes you need radiation therapy. But just want to mention, surgery goes all the way back to the 1800s. So that's something that's been done for a long time. The surgeons from Victorian time, they knew at that time already that if you remove the cancer, you had a chance to cure it. The problem, of course, is that that's very limited to cancers that you can access and to cancers that have not metastasized. So that's a very limited approach, but when it works, it can work quite well. There's radiation therapy that's really started in the early 1900s. The idea is that it kills specifically the cancer cells because the cancer cells divide faster. But again, it can be quite limited in terms of effectiveness, and it can be quite toxic and dangerous. Same thing, and it's similarly chemotherapy, which started in the late 1940s, and I'll say a few more words about that. Since they use the cytotoxic drugs, we're trying to find drugs that will specifically kill cancer cells and leave the normal cells alone. But that's been hard to do because after all, the cancer cells, they come from us. They're not some alien entity. So they have a lot of same mechanisms that our normal cells have, also found in cancer cells. So it's been a little challenging to find chemicals that are toxic to cancer cells and not toxic to normal cells. So that's why there's a lot of adverse effects, a lot of side effects when taking chemotherapy. And a lot of people think that the answer to these problems is targeted therapy or using targeted drugs. And the targeted drugs is sort of using our knowledge of cancer biology to target specific aspects of cancer cells that are not found in normal cells. And that's really a relatively recent advancement in cancer therapy. But of course, it's quite limited. It's not every cancer has a target that can be used for targeted therapy. So I think a big part of what we're trying to do is find new targeted drugs and find new targets in cancer cells so that we can use more of these targeted drugs and less of these other things here. And finally, the latest development that goes back 10 to 15 years is immunotherapy. I'm sure you've all heard about it. It's been incredible. Some of these, what immunotherapy has been able to do is been really fantastic. And basically what immunotherapy is using our own immune system. The immune system is always recognizing abnormal cells and eliminating them. But sometimes it fails. And a cancer might arise from that. So if we can sort of reactivate the immune system so that it can recognize cancer cells and destroy the cancer cells, then we could have an excellent therapy. And that's essentially what immunotherapy is. So when I was talking here about surgery and radiation therapy being sort of 1800 and early 1900s, this is a public service announcement from 1938 from the U.S. Public Health Service in cooperation with the American Society for the Control of Cancer, which became the American Cancer Society a bit later. And basically they were saying back then, the only safe weapons against cancer are surgery, X-rays, radium. So basically surgery or radiation therapy. There was nothing else in 1938. So the survival from cancer back then was very low. That we barely had any weapons. And by the way, the reason for this PSA is that there was a rise of people offering fake treatment at that time. People were quite desperate for new treatment. They didn't feel like things were going to work out for them, so they would seek new fake treatment. And there was plenty of sort of quack doctors who would offer these treatments to people, and obviously things wouldn't work out too well. So there was just a way to tell people, this is what we have right now that can work. Don't do anything else. But then, so the start of chemotherapy goes a little bit before this 1938. Is Paul Ehrlich showed that there was basically a chemical can treat and cure syphilis. So this was the first time that someone could give a human being a chemical and cure a disease. And that was sort of beginning, although this was not for cancer, obviously, but this was the beginning of the concept of chemotherapy. Maybe we can give people these chemicals that are either natural or synthesized, and we can cure disease. There was really two real breakthroughs that led to the sort of really early the foundation of chemotherapy. First, there was nitrogen mustard derivatives were studied and found to work against lymphoma. There's a little bit of an interesting backstory on this, and I'll give you the short version in a few minutes. And there's also Sidney Farber from Harvard. He demonstrated that aminopterin could produce remissions in children with leukemia. And this was the beginning of a completely transformative era for children with blood cancer. And I'll show you some graphs on that, and it's quite extraordinary. And so long-term remissions and even cures, many patients with childhood leukemia that were treated with chemotherapy were first reported in the 1960s. So that's when we sort of added one more arm to our weapons against cancer, chemotherapy. And then since then, many other cancers can be controlled with chemotherapy for long periods of time. Even sometimes the chemotherapy may not cure the cancer, but it may help to control it. And but unfortunately, a lot of times it can be quite toxic. So we need to move to better therapies. But that's certainly been a very important one. I just mentioned Sidney Farber and his discovery that aminopterin can treat childhood leukemia. And what's amazing, if you look at this graph here, in the early 1950s, in 1950, the 5-year survival for a kid with acute leukemia, whether it's ALL or AML, was basically 0%. The kids did not survive acute leukemia in the 50s. But based on his work, as well as other chemotherapies that were developed and used in combination, you have these survival rates, and that goes to 2010. The survival rates of 80%, and now it's even more in certain cases because we have immunotherapy that can work quite well against these diseases. So this shows how cancer research can really affect lives and make a huge difference. I did promise a little backstory on the meclorethabine, which was a drug that basically was developed in 1942, but it turns out that it's a DNA damaging agent. But it turns out it's a derivative of mustard gas, which was used in World War I as a chemical weapon. And when they studied what it did, they looked at the people who had succumbed from the chemical weapons. They would found that their blood was completely, that the fast-growing cells, the bone marrow cells in the blood were completely decimated. And that gave an idea to someone who was interested in cancer research. Well, maybe this could be used, obviously not at the same dose as these people saw during warfare, but maybe this could be used as a cancer therapy. And sure enough, some derivatives of mustard gas turned out to be fairly effective against some lymphoid malignancies. But obviously it's very toxic. If there are some chemists in the group, you see it's a very reactive molecule, and quite toxic. But it was used and was one of the first chemotherapeutic drugs. But how can we make cancer therapy less toxic? And I think, as I alluded to, is to use molecular targeted therapies. So targeted therapies, as I mentioned, so that they target specific molecules in or on cancer cells or in the tumor immediate surroundings. So this is a cancer cell that has sort of these really specific changes, and no cancer cell would have all of these changes at the same time, but this is just to sort of, portray what can happen. And one example here is a drug named Gleevec, which you might have heard of. It's used to treat CML. It works incredibly well. It's this drug with relatively low toxicity, and it's a pill a day, and people with leukemia can live just fine. And that's very, very targeted. So that's a good example of it, targeted drug. Similarly, you have Herceptin for breast cancer. It takes advantage of the fact that a lot of breast cancer have a receptor called HER2/neu on the surface of their cells. And then if you have an antibody, basically, that can go and recognize this and then kill the cells that have this on their surface, you can have a fairly specific way to kill cancer cells. So that's another example of chemotherapy. It goes and it finds something that's specific to the cancer cell and is not in the normal cell. And if you sort of push that a little further, if you think of, you could have patient A that has a mutation A, then you give that drug that corresponds to this mutation, and it kills the cells. It prevents the cells from multiplying. Same thing with then patient B may have a different mutation, but then you have a different drug for this mutation, and you treat this patient. with that drug, and that kills. So that's really how you can start thinking about personalized medicine, or what we also call precision medicine. And a way to sort of explain that and to illustrate this is to think of, let's imagine all these people have lung cancer. Everybody has lung cancer. In the past, we probably would have given all these people the same medicine. Whatever is the standard of care at that time, that's what these people would have received for the most part. But now, precision medicine can recognize difference in the molecular part of the cancers. They can recognize, wait, this person has a mutation, and we have a drug against this mutation. Let's put these people in a different category and treat them with a targeted therapy. And maybe these two there, or these three, have a different mutation. We can put them in a different category and treat them with a different drug. And that's going to be less toxic and going to work better. Then there may be the rest of the people that don't have any target. We can't find a target. Then these people would basically just go through conventional treatment because we don't have targeted therapy for them. The goal is to decrease this group of people to one day have a targeted therapy for everybody. That's sort of the ideal scenario that we hope that one day could happen. Whether it's possible remains to be seen, but that's the idea. We want we don't want to treat every lung cancer patient with the same therapy. We want to be able to understand their cancer and treat them with very targeted therapies. So then the next step is immunotherapy. And that's, as I said, it's been really revolutionary. And the idea here is to just use the T-cell, use the immune system to attack tumor cells. So it's just to harness the patient's immune system to provide durable and adaptable cancer control. This is what immunotherapy. So there's different types of immunotherapy. Don't necessarily, So those are all different types of chemotherapy. I just want to talk a little bit about adoptive cell therapy, adoptive cell transfer, which has been extremely worked well, and there's a number of approved therapies for this. And also, I want to say a few words about immune checkpoint inhibitors. And there's cancer vaccine, and there's many other approaches that are different types of immunotherapies. But for this presentation, I'll just want to talk about the two probably most important ones right now are adoptive cell transfer and immune checkpoint. Adoptive cell transfer, the idea of adoptive cell transfer is that you get a blood sample and you isolate the immune cell that basically the T cell that should attack the cancer, but they have not attacked the cancer. They're not doing what they're supposed to do. So what you do in the dish, you provide them with new weapons. And those are in the form of lentivirus that expresses chimeric antigen receptor. And it's not that important to understand what that is. The point is those are spike on the surface of these T cells that can then recognize the cancer. And then what is done is that these cells are amplified and re-injected into the patients. And now, starting from these cells that couldn't do much, we're injecting in the patient sort of an army of T cells that can attack the cancer. And this is what adoptive cell transfer is. Another type of adoptive cell transfer is the TIL therapy, which stands for tumor infiltrating lymphocyte therapy. This is different. Instead of taking the cancer patient's blood, we take the patient's cancer and we isolate the T cells from that cancer. So now the infiltrating T cells, it's a sign that these T cells are trying to do something to this cancer, but maybe there's not enough of them, or maybe there's not as efficient as they should be. So taking from these T cells that are already in the tumor, we take these T cells and we amplify them. Basically, we just make more of them and we re-inject them, hoping that this increased number, and there's ways to engineer them also, that can then, these new cells, they're reinvigorated, can then go and attack the cancer more efficiently. So these approaches, especially CAR T cell therapy, have been extremely successful, and patients have been cured of cancers that were thought to be incurable using this approach. And then there's the immune checkpoint inhibitors that are also been incredibly successful. And what these do, they basically restore sort of the immune brakes. The immune system has a set of brakes to make sure that the immune system doesn't turn against ourselves. But sometimes these immune brakes are a little too strong, especially in the case of cancer. We'd like to release these brakes again so that the tumor cell, so that the immune cells can attack the cancer. And this is what these immune checkpoint inhibitors do. They basically release the brakes. And this is from the 2020, so it's from a few years ago, but it just goes to show all the FDA-approved immune checkpoint inhibitors at this point. And these drugs are, especially in melanoma and in many of these cancers, have been incredibly useful and worked extremely well at curing cancer that, again, were thought to be incurable. So these advances have been just really mind-boggling for the field to be able to use these drugs and cure patients that normally were thought of as incurable. I'll say a little bit about clinical trials. I think I have a little bit more time, maybe 5 minutes or so. Does that work? Or I could skip some of what I have if I'm starting to be a little on the late time. Okay, so it won't take too much longer. But so I want to talk about clinical trials because it's such an important part of cancer research. And since I've been talking about historical aspect of all this, I'll talk just a few words about the first, what is often thought or referred to as the first clinical study. It was James Lind, was a Scottish Navy surgeon, and of course scurvy was a big problem for sailors in the 18th century. And he was on a trip one day and he decided to conduct a little study. He took 12 scurvy patients and separated into 6 groups and gave them something. Each group received something different. And what he found is that the group that received the oranges and the lemon actually recovered. Now we know it's because there's vitamin C in them, and it's a well-known fact now. But back then, he sort of used what we could see as sort of an ancestor of a clinical study to figure out what's the best thing to do to treat the patient. Of course, there were 2 patients that received vitriol, which I assume didn't do too well. I don't think I would have wanted to be part of that group, but so now we're a little bit more advanced. I don't think we would have a group that receives poison as part of clinical trials. But without spending too much time, there's the preclinical aspect of this, which is so important, the lab studies. I mentioned the importance of that. But once we have good leads, they go through these phases, several phases of clinical testing. The first one being just to evaluate safety, but then it gets more and more specific. And in phase 3, we look at the efficacy as well as can be compared against existing drugs. Is it really better than what we already have? And then after a successful phase 3, that's when we get FDA approval. But then that's what we call phase 4, where the FDA continues to monitor what happens with these drugs. Is it really as good as we thought it was? So that's really sort of an important part of this whole clinical testing. And I don't need to go over this, but so basically, the people sometimes ask me, should I participate in a clinical trial? And maybe there's sort of pros and cons to be in a clinical trial. In my opinion, the pros outweigh the cons significantly. But the thing is that you'll never get less than what you would get in terms of standard of care. They would never not give you a drug that you should get, but then you might get more. So the benefits of a clinical trial is that you have access to promising new approaches that you wouldn't get in a regular clinic. And so a lot of close monitoring of your condition, because they want to really know what's happening with the trial. But the drawback, of course, is that it may not really work, or there may be some side effects that people don't know about yet that will be uncovered. But I think in addition to potential benefit to yourself, there could be benefit generally to cancer research in general. If it doesn't help you, maybe you're participating in a trial might help the field or might help the next person who has the same disease. So a few quick words about prevention, which is a very important part of cancer research, although the research on prevention is not as developed because it's a very difficult aspect of cancer research, but prevention itself is very important. As I mentioned earlier, I showed you this graph in terms of the different cancer rates per 100,000 according to time, and you see lung cancer increasing really fast and then decreasing. I think we all know what that's for. The reason for that, in the 30s and 20s, lung cancer was relatively rare, was not a very common disease. But because of smoking, and it's been really clearly associated with smoking, the lung cancer rate have increased until there's been sort of a reduction in smoking in the past 20, 25 years, and then the rates are starting to go down again, which has led to a very large, just the smoking cessation efforts have saved a large number of lives. There's no question. So that's sort of prevention aspect of lung cancer, and even today, about not every person with lung cancer is a smoker, but it's believed that about 90% of all the lung cancer cases are due to smoking. Stomach cancer, why did it go down? Well, people think it's because of refrigeration, which became more common starting in the 20s and 30s, and people didn't have to smoke their food or salt their food as much. Two things that can be associated with stomach cancer, and also there's been a decrease in Helicobacter, a bacteria that's associated with stomach cancer. So this shows that there are things that can be done. It does, you can't just by having a good diet, you can ensure that you won't have cancer, but you can certainly decrease your risk by having, let's say, a better diet and exercise. These type of things have been shown, and these type of graphs show that a cancer rate is not a fixed thing in time. I'll skip this. I've already made the point between lung cancer and cigarette, and this is a little bit more of the same here. There's also an idea of chemo prevention, and this is like, the same way we can take drugs for chemotherapy to treat existing cancer, are there drugs we could take to prevent cancer before the cancer is even there? And the answer is probably yes, we'll be able to develop these type of things. And a good example is NSAID, these non-steroidal anti-inflammatory drugs, like aspirin or ibuprofen. And they've been shown to reduce the risk of colorectal cancer. And there was even a suggestion that it may be worth taking a baby aspirin every day after the age of 50. But because of potential side effects, especially on the stomach lining, this is no longer a recommendation, but it could be useful for a certain population. But also, I think it is sort of an indication that it might be worth trying to develop better NSAIDs that may not have as much side effects, but they may still prevent and reduce, not completely prevent, but reduce the risk of colorectal cancer. And early detection, another very important aspect. Why is early detection so important? Just look at the survival rates if the cancer is detected early versus detected late. Cervical cancer, detected early, 93% of the women survive. Detected late, 15%. Breast cancer, 93 to 6. Colon cancer, if it's a stage 1, 74% survival. Stage 4, 6%. So, and same thing with melanoma. So early detection is so important. We want to detect cancer before it's a real cancer. If we could detect it in its earliest stages, this is when screening could be most important. And I just showed you the importance of early detection. But there's a number of traditional methods that are working quite well, mammography, colonoscopy, biopsies like the Pap smear. But there's new emerging technologies being developed that are really revolutionize early detection. Liquid biopsy. Can we find signs of very early cancer in the blood? Breath test. There's ideas that maybe you can breathe into an apparatus that would detect signs of cancer. Advanced imaging techniques that can detect the smallest forms of cancer. and nanosensors. It's almost in the area of science fiction, but it's incredible what these things can do now, and they're being developed. And I just wanted to finish with AI, since everybody is talking about AI these days. But basically, what's the role of AI in cancer research? Well, I think it will have a role in basically everything I've presented today. It will be able to improve basic research, maybe come up with better protocols, better at analyzing existing data, so on. So I think that the use of AI will be really, I think is already making a difference, and it will continue when you think about early detection, diagnosis, recognizing patterns on slides, diagnostic slides, whether it's drug discovery and development. How can we optimize? Like, maybe we don't need to screen 5,000 compounds. Maybe AI can kind of say, these 4,000 are just a waste of time. They're not going to work. Just screen 1,000 compounds, and then it would really accelerate, the discovery. And same thing with these other aspects here, whether it's clinical trials, can they be optimized using AI, and so on. So I think it will really revolutionize the way we do cancer research, and it has already started. So I think I'll stop here, and I think hopefully I'm pretty close to my time, and I'm happy to answer any questions you might have.
Can you hear me?
Yes.
We're going to ask people in the audience to raise their hand, as Professor Aho has done.
Al,
Al, yeah.
can you hear me?
Yes.
Thank you for a very fascinating talk. One of the questions of interest is, I was a professor at Columbia University, and I always wondered, what should I be teaching my students? So what should we be teaching the doctors of the future on how to detect and prevent cancer?
Yeah, this is such a good question. I think what I find is that a lot of times the younger students don't understand the sort of the emerging technologies, and are not as willing to use them sometimes. So I think an important part would have classes that really talk about what is happening now and what will be happening in the future, and really think about personalized medicine is I think so important. Like, no two people are the same, and for way too long, in my opinion, cancer patients were treated as a group. If you have lung cancer, here's what you're going to receive. If you have something else, so I think another important aspect is really to tell the students to think of their patients as individuals, spend the time that they need to talk to them, to really understand, but also really understand what their disease is. And that's also, in a way, connected to the idea of just being open to all these new techniques, new technologies, and really use them.
Chris Jager?
Yeah, when you discussed the progression of cancer, maybe a third of the way through your presentation, you mentioned genetic changes. Is that in the particular cells that we're talking about becoming cancerous, and how frequent is that? How often is that strange genetic change a driver of whatever cancer it might be?
Yeah. So again, a very fantastic question. So there's been a number of studies that have been done to address this. So first of all, you need to understand that it's not just, I think, as I mentioned, it's not just one mutation that causes cancer. It's a series of them. You need one, then you need the other, and the other, and the other. And a lot of times they also need to be in the right order. So if you have these mutations in the wrong order, it doesn't really happen. So for all this to happen in a very coordinated way, it's all about luck. It's or bad luck in this case. So it's not, it doesn't happen very often. If you think about this, because cells in our bodies, they divide all the time. And each time a cell divides, there's an intrinsic error rate in the DNA replication. So each time a cell divides, there's a chance that there will be a mutation. But the mutation can be anywhere. So it's a random mutation. So when the mutation happens to be in a gene that may lead to a cell to grow a little faster, then this mutation may be selected. So the mutations themselves are pretty frequent, and they can be even more frequent if for smokers, for example, because there's a lot of carcinogens in smoke, or people who go to the sun, and the UV light of the sun can accelerate the rate of mutations. But as I said, there's an intrinsic mutation rate that is relatively high. But then it also needs to be at a very specific place, and it also needs to be placed in sequence of other mutations. So because of that, overall, it may feel like cancer is a very frequent thing, but if you really think about it, considering the lifespan and considering the number of cell division that takes place in our body during our lifetime, cancer is not a very frequent event. But it does happen when all of these mutations happen, you know, in a sort of sequential type of fashion, and also in a very specific cell.
Mike Jets?
Thank you for a great presentation. It was very informative and enlightening. Question I have, you mentioned in one of the slides regarding clinical trials, a disadvantage of that can be the cost of the patient, and that may not be covered by managed care plans or insurance. My question is, aren't a lot of the costs of this subsidized by drug companies and perhaps institutions such as NIH that fund them?
That's correct. Like for the vast majority of clinical trials, all of the costs will be covered by the sponsors. So that's another advantage. There could be some cases where it's not going to be. There could be some cases where there's some. For example, if the clinical trial requires additional tests that you need to go to the hospital for, it may be sometimes maybe difficult to get that covered, like your transportation, you know, things like that. But for the most part, a clinical trial, everything that's connected to the scientific part and to the clinical trial itself will be covered by the sponsor or by other entities funding the trial. As you said, it could be NIH, it could be other, but yeah.
Ron Folk?
Thank you very much. That was a very interesting presentation. My question is, where is the research work that's sponsored by the Ludwig Foundation actually being carried out?
Yeah, so we have three branches, and that has changed over time. So as I mentioned earlier, the Ludwig Institute for Cancer Research was founded in 1971. There's been some branches that opened and that closed over the years based on, as I said, based on opportunities. We're trying to make sure that we always fund the most exciting and the most impactful science. But right now, we have three branches. One is in Lausanne, Switzerland. One is at Oxford in the UK, and the other one is at Princeton, New Jersey. So those are our three branches where we're very focused right now. And they all have sort of different specialties sort of that they focus on. And we also have 6 centers. We have one at MIT, one at Harvard, one at Johns Hopkins, one at Memorial Sloan Kettering, one at Chicago, and one at Stanford. So, and again, the idea is to provide funding to these centers to supplement what they're already doing. We're not building new buildings, we're just providing, okay, you already have a great program, we can provide additional funding so you can make it even greater. So, but those are the sites.
Alberto?
Yeah, thank you very much for your presentation. Fantastic, very clear, and I think it's very understandable for many people that are not in the science area. How do you consider which one evolution in the treatment of cancer is for you the most, hopeful and interesting in the near future? Well, let's say medium term, 10 years from now? Is it the correction of genetic, mutations? Is it development of new technology to detect cancers? Is it what is it?
Yeah, that's a really great question. So the way I see it is really twofold. I think we need to do better with early detection. Early detection is the key. So and there's these really incredible new techniques being developed for early detection, whether it's liquid biopsies, which I didn't really have time to talk about too much, but you can detect cancer cells, or you can detect DNA from cancer cell in a patient's blood. Can we increase the sensitivity of these techniques where we can find a tumor where it's very, very small? And can this tumor provide a fingerprint just from the sequencing of a little piece of DNA from the blood? You'd be able to say, oh, this person has a very, very small lung cancer, or this person has a very, very small pancreatic cancer, or something like that. So this could be incredibly powerful, because treating a full-fledged cancer is very difficult. It's always, I mean, we're able to do it and we cure some cancers, but as I showed you with the stats at the end, the difference between early and late, it's striking. Curing a full-fledged advanced cancer is very, very hard. Curing a very early cancer is doable. We do it all the time. So this is, I think, to me, the most exciting part is really to try to increase our early detection approaches. Like there's new technology, whether it's nanosensors, things that can go and find the tumors and then you can detect it. Things like that are science fiction now, but 10 years from now, it may be something that we do routinely. So that's the part I'm most excited about. Obviously, I'm excited by immuno-oncology and immunotherapy, which has been incredible. What it does, I think 20 years ago, if you told someone that you could treat a patient with advanced melanoma with an immunotherapy drug that has basically no side effects and the cancer is wiped out, completely gone, people would have said that's impossible. It can't happen, but it does. So that's exciting. But to me, early detection, because of what it can do to avoid even having to treat cancer, you take care of cancer before it's even cancer. And that's hopefully the future. And hopefully we'll be able to do that.
Yeah, wonderful talk. Very, very insightful. And of course, a lot of questions do come to mind. So there's one that always puzzles me, and maybe you're the guy to ask. For the most part, we think of cancers, and throughout your talk, also, you talked about cancers occurring because of random mutations during cell replication, random gene mutations. And this is just intrinsic to the process of cell replication. There might be Darwinian reasons for these things happening, But anyway, but then there's the question of carcinogens. And you talked about carcinogens. And so we think of smoking causing lung cancer. So to what extent so maybe there are certain cancers that are actually caused by chemical or maybe biological agents that enter the body, as opposed to purely random processes. Or maybe you're going to say that smoking doesn't cause cancer, but it changes the probabilities and so on and so forth. It's a contributing agent or something like that. So to what extent are cancers caused by carcinogens?
Yeah, so it's a very obviously complicated question. If we focus on lung cancer, for example, what's interesting is that carcinogens, they leave a trace in the genome. The type of mutations that are caused by carcinogens can be a little different than the type of mutations that are caused by random replication errors. So you could kind of tell this cancer was really exposed to high levels of carcinogen, and you may be even be able to recognize in some of key genes a mutation that looks more like a mutation coming from a carcinogen. So there are some cases where you can tell, and some cases where you probably can't tell. You know, maybe a smoker gets lung cancer, but maybe this person would have had lung cancer anyway because they had a mutation that was not due to the carcinogen, right? So those are a little, you know, difficult to completely tease out, you know, what is what. But as I said, there's no question that carcinogens significantly increase, orders of magnitude increase the rate of mutations in the genome, and you can see it in how people get various cancers too, right? Like, as I said, lung cancer was almost not a thing in the early 1900s, but I think after World War I, a lot of the people came back. A lot of the soldiers came back with a smoking habit. They brought it back, and and it's not the only source, but the smoking really increased during those years. And then there was a lag of about 15, 20 years, and then there was a lot of increase in lung cancer. So clearly, carcinogens will increase the rate of mutation, which will then increase the rate of cancer. But having like a real sort of one-to-one, for example, someone that's, let's say, someone has prostate, let's say someone has prostate cancer. Can you 100% know where is it just a replication error, or was this prostate cancer cell in contact with some carcinogen at some point for whatever reason? You know, so we don't really, that can be questions that are hard to, you know, for individual, but as a group, there's no question that, you know, carcinogens are causing cancer. I don't know if that, hopefully that answers your question.
Mike Martin?
Yeah, hi. Thank you for a great talk. I have two questions following up with what Paul indicated.
Yeah.
One is my understanding of certain cancer types, there's perhaps hundreds of genetic mutations associated with it. On the surface of that, this idea that somehow you can alter mutations through CRISPR therapy and these types of approaches, it seems rather daunting, if not impossible. So that's the first question. Mm-hmm. Adding to the complication is essentially in mutations. So you have a mutation from a lung cancer. The genetic mutations contained in a metastasize are different from the parent compound or the parent tumor in the lung. So essentially what we're doing, we're trying to hit moving targets, a multitude of targets, which seems to be daunting. And I guess those two factors, if you could just talk about metastases and the nature of mutations in the parent compound. Thank you.
You're 100% right. You're 100% right. That's one of the questions and one of the challenges with trying to treat metastatic cancer is that in a way they start to evolve independently. They're in effect different cancers with different mutations, and that's one of the problems sometimes with even the targeted therapy. You may have mutations that you find in the original tumor that is either no longer, or you may have a mutation, let's say in one of the metastatic sites that's not in a different one. So you would have targeted therapy that works for one tumor, but not for the next tumor. And even within the original tumor, there can be some heterogeneity in the mutations that make treatment very, very difficult. So you're right. It's a moving target, very, very difficult to treat, and that's definitely one of the challenging. That's why sometimes immunotherapy works well, because it may recognize more generic targets, but also for targeted therapy, a lot of times what people try to do is find a target that's completely essential for cell growth. So for example, you have in lung cancer, you have RAS mutations that are considered to be very important for cell growth. So for the cancer growth, so the cancer can't really lose that mutation. They can't just get rid of it. So if you can find a drug that attacks this exact mutation, you either kill the cancer, or if the cancer loses that mutation through evolution because it's kind of selected against because of the drug. If they lose it, they still can't grow because they needed it anyway. So that's kind of a way to go around that. But I think you're 100% right. That's the big challenge of trying to treat cancer because of the heterogeneity and how quickly it evolves. And that's probably why we can't cure a lot of cancers right now. Your other question was about CRISPR, and I completely agree with you as well. There's so many changes, and cancer cells, the cancer genome evolves so rapidly that trying to use CRISPR to restore, to revert a mutation back will be very, very challenging. I think some people are trying to do that. I personally not confident that the approach will work, but we never know. The other challenge, of course, is that with CRISPR is that you need to change the let's say you want to revert a mutation. There's a mutation somewhere in the genome, and you have a tumor mass with, let's say there's 1 million cells. You need CRISPR to go and change this mutation in every cell, because if it doesn't, if you leave 10, 15 cells behind without being reverted through CRISPR, these cells will just take over again. So it's a real challenge, delivery, and also making sure that a lot of the cells have the reversion. So I think the CRISPR type of approaches, genetic, will be quite challenging, but time will tell. I hate to say something is impossible or will not work, because people have been proven wrong over and over. So we'll just have to wait and see. But I think it will be challenging.
Yeah, thank you for a wonderful presentation today. I have 2 questions. I wonder if you could expand on the status of vaccine research in terms of cancer. Wonder if there's any specific cancers that it seems to be more promising than others. And my second question would be, what role do you see artificial intelligence playing in the future research of cancer?
Yeah. So cancer vaccine, it's a very active field. The idea is that basically, from a very simple terms, is you're trying to boost the immune system to recognize the cancer as if it was an outside, like an infection. So that it would go recognize it and kill it the same way it kills, a virus. And there's many ways to do this, and it's being attempted for a number of different, basically every cancer you can think of. There's probably a group out there trying to develop a cancer vaccine. The problem is often the target. What is the best target to that you're going to direct your vaccine against? So that's a challenge. You want to make sure it's something very specific, and that's found in every cancer cell. But I've seen papers recently that have shown maybe some promise in the field of ovarian cancer, for example, where they had this sort of cancer vaccine. They vaccinated women, and then they treated them with CAR T-cell therapies, and there seemed to be an increase or an increase in response. But so far, it's quite limited, so it remains to be seen. I know there's a lot of activity in trying to develop cancer vaccine against breast cancer, and against some specific antigens that are found in breast cancer. So it's it's another very active field, and I think it's quite promising too. I think there could be ways where that, and maybe in combination with other types of approaches, will lead interesting new approaches, but we're not quite there yet. Oh, and you also had a question about AI. Sorry. So I think as I try, I know I didn't spend much time at the end there about AI, because everything is developing, but it was interesting because as I mentioned at the beginning, I'm also director of communications for Ludwig, and we have a magazine that comes out a few times a year. If you're interested, just send me a quick email, and I can put you on the mailing list. But it really talks about the discovery of the Ludwig researchers. But we have a section at the end of the magazine, and we call it Ask a Researcher. And our last question, or maybe the one before that, was, how do you use AI, and how do you think AI will impact your research. And it was really fascinating what we received, because basically everybody saw it a different way. So people from lab thought that AI could help them plan their experiments better, or if they had a lot of data, they generate. So a lot of these experiments now, whether it's what they call that single cell technologies, will generate huge amounts of data that are very hard to interpret. They think that AI may help them analyze all these data, because AI, you don't need to have an hypothesis with AI, right? The AI can learn from your data set. So this is what people really think that it will help, but it can also help in the diagnosis of cancer, be able to screen slides a little faster, or be able to go through people's EHR and really understand, recognize signs that people may be, more likely to have cancer in the future, just based on what's in their medical records, for example. So there's just so many, or help with clinical trials. The clinical trials typically generate a lot of data that can be sometimes a little difficult to analyze, and I think AI can help with that. Can help with the planning of new trials and so on. So it's almost like, and also, for example, I think, as I mentioned, in the development of specific drugs, I think there might be a way that AI can recognize the molecular structure of some drugs and say whether this is promising or not promising, and sort of accelerate the discovery that way. So there's just, I think, in a way, your imagination of what it could do is basically what it could do. There's just so many different ways, and hopefully, if it doesn't take over the whole planet, it will help us cure cancer.
Okay, Tom?
Is there a national protocol for handling the different types of cancer? Because how can you assess the treatment if they're not treated the same way throughout the country?
Yeah, so this is, I mean, honestly, this is a bit outside of my area of expertise. I'm not a medical doctor, more on the research side, but my understanding is that there are standard of care that are recommended by a number of organizations that do just that. So yeah, so there's, like, typically there are ways that most patients are treated, but there's some flexibility within these recommendations. So sometimes you may have, lung cancer patients are not, there's recommendations on how it should be treated, but there's also some leeway. Some people are some people might react really poorly to certain drugs. So some of these drugs may be withdrawn from a cocktail, for example, so there's some flexibility, but at the same time, there's really clear protocol as to how people are treated for certain cancers. And it all has to be approved by the FDA. So it's not like all of a sudden you can give out of the blue a drug that's never been given for lung cancer. You give that drug to someone, you can't really do that. So there's sort of clear things that can be done and things that can't be done.
Tom, can you close off the program and thank the presenter?
Okay. Pat, thank you very much for this presentation. There's two ways we thank people. One is the Old Guard certificate, which we will send to you.
Thank you.
And if you see the certificate, it's because this summit was the Center for Growing This for many, many years. And the second is the Old Guard salute, which is a thank you for all the work. So we really thank you and appreciate your help.
Thank you. It was my pleasure. It was very nice. And thank you for all these wonderful questions.